in this video, we're just going to sum up the big points that you were supposed to come away with after completing those first two problems, 8.1 and 8.2, out of the section 8.1.1, titled How Can I Put Them All Together? So earlier in the year, we did study transformations, but if you remember, we very intentionally told you we were not combining horizontal shifts with horizontal dilations because that just kind of bumps the difficulty level up a little bit. Well, now we're ready to actually look at them together and figure out how do we deal with a function that has both horizontal shifts and horizontal dilations. So in those first two problems, you had Laurel and Hardy's attempts at writing equations for a sine function that had a modified period and also had a shift. We were looking for a period of 2 pi over 3. So that wasn't really addressed as much. So let's just real quick kind of see how that works in both Laurel and Hardy's equations. Well, if you remember, the formula for period is 2 pi over b. In both of these forms, the b is 3. So both of these equations would end up giving you a sine wave that had a period of 2 pi over 3. But it's the horizontal shift that is different. Let's think about the parent function, y equals sine x. That function, being the parent function, would have no horizontal shift. And we know the horizontal stuff is always happening with the x. So what I've written here is x equals 0. That just really represents no horizontal shift. I'm just pulling this x out here and saying there is no horizontal shift. So the equal 0 is just a way for me to understand no horizontal shift is happening in the parent function. So now let's look at Laurel and Hardy's equations. Now if you've noticed, I boxed in the x on y equals sine of x. I'm going to use the word argument. That's a word I've only used a few times this year, and it's a word I'm going to be referring back to through this lesson. So whatever we're taking the sine of, or it can be cosine or tangent, whatever we're taking that function of is what we call the argument in mathematics. So in Laurel's equation, the argument would be 3 times the quantity x minus pi over 2. And in Hardy's equation, the argument would be 3x minus pi over 2. So if we wanted to see the horizontal shift in either of these, what we're going to do is take that argument, set it equal to 0, and then solve for x, and that's going to reveal the horizontal shift. So you can see I set Laurel's argument equal to 0, I solved for x, and I got pi over 2. So when I'm relating that back to this equation that I wrote in the beginning to illustrate that the parent function has 0 horizontal shift, what I'm seeing now is that Laurel's equation, because the argument when I solve for x is equal to pi over 2, that is just telling me that this has a shift of pi over 2 to the right. When I do the same thing with Hardy's equation, when I take the argument, what we're taking sine of 3x minus pi over 2, when I take the argument, I set it equal to 0. 0 just meaning no shift. And then I solve for x, I see that there was a shift to the right of pi over 6. So really, picking the right equation comes down to just knowing your order of operations. So order of operations do affect transformations, and we're going to have to keep those in mind as we continue writing equations to represent transformed sine and cosine functions. So let's look at just a generic problem together to go back over the skills we were just talking about. I have the equation y equals cosine of 4x plus pi, and I want you to identify the transformations. So hopefully you recall that the 4 in front of the x, that represents the frequency. It tells you how many cycles are going to occur over a span of 2 pi radians. And we're using 2 pi because that's the period of the parent function, y equals cosine of x. So in this function, we would have 4 cycles every 2 pi radians. So to get the period, we'll use that formula 2 pi over b. Period equals 2 pi over b. So we said 4 cycles every 2 pi radians. So we would need to cut 2 pi into 4 equal pieces to get the length of a single cycle. 4 cycles in 2 pi radians. 2 pi divided by 4 will give me the length of a single cycle. So that's going to be pi over 2. So this function has a period, or will complete one full cosine wave over a span of pi over 2 radians. So let's move to really the heart of today's lesson, the horizontal shift. Remember, to identify a horizontal shift, we want to take the argument, or what we're taking cosine of in this situation, take the argument and set it equal to 0. Again, that 0 is just representing the parent function having 0 horizontal shift. So it would look like this. And now we're going to solve for x, and then our solution just reveals the amount of horizontal shift we have in this equation. So when I do that, I get x equals negative pi over 4. So that represents a shift to the left of pi over 4. So let's tie this all together. Let's sum this up. What I have here is just our general form that's going to be helpful as we're working through transformations of trig functions. Now I have the cosine function in there. You can replace that with the sine function. Everything would stay the same. So I've copied down that original function that I used in this example. I want you to look closely. Is this function really in that exact form? Hopefully you notice that it's not quite there. If you look at the purple form, you'll notice the b value is factored out. And in this form, in y equals cosine of 4x plus pi, the b is not factored out. So to get this into that transformation form of the equation, let's go ahead and factor that 4 out and rewrite this as an equivalent equation. So it's going to be set up something like this. So remember, factoring out, you want to think I'm dividing both of those terms in the argument by 4. Whatever's left is going in those parentheses. And here's that final result when you factor the 4 out. So I want you to look at this and look at the value for the horizontal shift that we got using that set the argument equal to 0 method. You should be seeing that either way is going to give us the same answer. This right here represents that horizontal shift to the left, pi over 4. So make sure that you become very familiar with this purple form. This is called our transformation form for a trig equation. You want to make sure that you can take any equation we give you and write it in this form, making sure the b is factored out. And once you do that, all of the transformations are going to be visible to you. That k value at the end, that's going to represent your vertical shift. The h inside the innermost set of parentheses, that's going to represent your horizontal shift. The b value, that is creating some type of horizontal dilation, either horizontal stretch or shrink, which as a result affects the period. Notice I didn't say b is the period, b affects the period. So 2 pi over b is what you would use to actually get the period of the function. And then finally that a out front, that gives away two things, both your vertical dilation, either a stretch or a shrink vertically, and then also if we see a negative there, we know we've had a reflection.